All right, today we are jumping into a really fascinating mathematical detective story. And I mean that. It's a story that genuinely took over 150 years to solve. It's all about the most mysterious, the most fundamental numbers in the universe, the prime numbers. And at the heart of it all is a breakthrough that was both brilliant and, just stunningly simple. So let's get right into it and start with the central mystery.
So here it is, the big question that has totally captivated mathematicians for centuries. Are prime numbers random? I mean, when you look at a list of them, they seem to pop up without any real pattern or reason, right? But is there some kind of hidden order to all that chaos? Well, that's exactly the question we're going to investigate today.
Okay, so let's do a quick refresher, just so we're all on the same page. Prime numbers are basically the atoms of the number world. They're these indivisible building blocks like 2, 3, 5, 7, and on and on. Every other whole number can be built by multiplying primes together. But the thing is, they don't follow some obvious sequence, they just appear. And trying to figure out the rules behind their appearance is one of the greatest quests in all of mathematics. Now, this mystery didn't just pop up out of nowhere. The hunt for a pattern in the primes had been going on for over a century before our main character Mertens even enters the scene. Some of the greatest minds in history had found clues, little whispers of a pattern, but nobody had quite managed to put all the pieces together.
Yeah, this investigation was a real slow burn. Way back in 1737, the legendary Euler, he had a sense of how primes behaved on average, but his methods were a bit fuzzy, using ideas like the logarithm of infinity, which, well, it's not exactly rigorous. Then you have Legendre, who came up with these formulas that looked right, but they were really just based on intuition, not solid proof. Even the great Chebyshev made a huge leap forward, but his entire proof was balanced on a big assumption that he couldn't actually prove. It took another 45 years to prove that. So you see, each one got a little closer, but that final rock-solid proof was still out of reach. And this is a really key part of the story. Our hero, Franz Martens, he didn't just pretend to invent these ideas from scratch. No, he very diplomatically acknowledged the work of the people who came before him, especially Legendre. It's a great reminder of how science and math are really a team sport, one that's played out across centuries. And that brings us to 1874. This is the year Franz Mertens publishes his masterpiece. And he didn't just provide one little insight. He delivered this trio of theorems that, together, painted the clearest picture of the world of primes that anyone had ever seen. So Mertens' first theorem was really all about control. It was about proving there's an underlying order. What Mertens proved is that a special kind of weighted average of the primes never strays too far from a simple, predictable value. It's like he put up a mathematical fence, proving that the primes thin out in a controlled, predictable way, not in these huge, chaotic bursts. The second theorem, though, gets even more precise. It looks at the sum of reciprocals. So that's 1/2 plus 1/3 plus 1/5, and so on for all the primes. Why do this? Well, this sum tells us a lot about how dense the primes are. Mertens proved that while this sum does grow forever, it grows with this astonishingly slow rhythm of the log of n. And to give you an idea of just how slow that is, for log n to get to the number 4, n would have to be a number bigger than 1 followed by 23 zeros. It's just unbelievably slow growth. And then you have the third theorem, which is just pure mathematical elegance. Mertens took this infinite product that involves every single prime number, and he showed it settles on a very specific, very famous number. And that number is built from two of math's most important constants, E, which is the base of natural growth, and gamma. He basically connected the entire seemingly chaotic set of all prime numbers to a single, beautiful, fundamental value. It's just amazing. So Mertens proved these three incredible results. But honestly, the most remarkable part of his story isn't just what he proved, it's how he proved it. This is where you see his true genius really shine through. See, at the time, the absolute holy grail of number theory was something called the prime number theorem. It was supposed to be a precise formula for estimating how many primes there are up to any given number. This was the big one. This was the problem everyone was trying to solve. Now, what's so wild is this comparison right here. The prime number theorem was finally proven in 1896, and it required some incredibly powerful and advanced mathematics. We're talking complex analysis and the famous Riemann zeta function. But look at Mertens. 22 years earlier, he achieved results that were almost as strong.
but he did it using only elementary self-contained methods. No unproven assumptions, no crazy advanced math. It's like everyone else was trying to conquer a jungle with heavy machinery, and Mertens just found a simple, elegant path right through it.
So you might be asking, why are we still talking about a 150-year-old proof? Well, it's because Mertens' legacy is far from over. His work didn't just solve a problem, it opened up entirely new ways of thinking that are still incredibly relevant today.
For one thing, his formulas aren't just beautiful, they're unbelievably accurate. The difference between his formula and the real answer is tiny, and it just gets smaller and smaller as the numbers get bigger. But this amazing precision actually brings up another, even deeper question. So the error in his formulas is tiny, for sure. But is it a consistent error? I mean, is his approximation always just a little bit of an overestimate, or is it always a tiny bit of an underestimate? For decades, nobody was really sure.
And this just brilliantly shows how deep mathematics can be. Because in 1983, more than a century after Mertens, a mathematician named Guy Robin proved something absolutely astonishing. That tiny error, it isn't fixed at all. It actually changes sign infinitely often. It's a never-ending dance, oscillating forever between being slightly too high and slightly too low. It just goes to show you, even inside a solved problem, there can be deeper, wilder mysteries. And his work is still very much alive in modern fields. Mertens' third theorem is actually a foundational idea in what we now call sieve theory. This is a powerful set of tools used in probabilistic number theory to estimate the chances that some very, very large number isn't divisible by any of the small primes we already know. So this elegant idea from 1874 is still helping us explore the frontiers of math today. So, in the end, the story of Mertens' theorems shows us something really important. It shows that progress isn't always about using the biggest, most complicated tools you can find. Sometimes a profound and lasting insight comes from finding a path of elegant simplicity. Mertens proved a deep order exists in the primes, but in doing so, he also revealed new, subtle layers of complexity, leaving us with this one last, tantalizing question. What else is out there, hiding in plain sight, just waiting for the right person to look at it in a completely new way?